This is an example of circular motion.
And I'm going to calculate centripetal force for my giants, or what I was doing on the bars. And first, I start out by finding how tall I am, and I'm 1.6 meters tall because I'm 5'3". And then to find the circumference, I do 2 pi r, so that's 1.6. And then that comes out to be 10.05 meters. And then I found how many seconds it took to do one rotation, and that was 2.402 seconds. And then I do circumference divided by seconds, and then that gives me my velocity, which is 4.18 meters per second. And then to find the centripetal acceleration, I do velocity squared over radius, and that's 4.18 squared over 1.6, and then that's going to give me 10.948. And then if I want to find centripetal force, I do 10.948, which is my centripetal acceleration, and then I multiply that by my weight, which is 58.89 kilograms. And then that gives me 644.73 kilograms meters per second squared. And then that's my centripetal force. So I weigh 130 pounds, which is 58.89 kilograms. And the Earth pulls me down at 9.81. So, okay. So the force diagram for me standing on the ground would be me. And then since I weigh 58.89 kilograms, that means I'm pushing down on the Earth with 577.7 newtons. And then the Earth is pushing up on me. These are congruent with 577.7 newtons. Okay, so I'm pushing down on the beam with 577.7 newtons, and the beam is pushing me up at 577.7 newtons because I'm not moving, so it has to be equal. And then when I jump off, I'll be in free fall, and the Earth will only be pulling me down with 577.7 newtons. And then when I hit the ground, it's like the ground is pushing up with that many, and I'm pushing down. Okay. And then when I jump off the beam in free fall, my force diagram looks like this. And it's not balanced, which means I'm accelerating. And you can tell because I'm moving towards the ground. Okay, so I'm going to do a force diagram for me hanging from the bar. And then this is what the force diagram will look like. So this is the force diagram of me hanging from the bar, and as we found before, the Earth is pulling me down with 577.7 newtons. And then I found the angle between my arm and the horizontal to be 73 degrees. So this will just be a dotted line. And since my arms are the same length, it's even. And then I know that these two have to be half of this because they need to add up to it. So it's 288.8 newtons is this vertical one. And it's the same on the other side. And then I can find out using trig that this is 88.31. And then my arm is pulling me up with 302.05 newtons. And then it would be symmetrical for this side. So this is pulling me with another 302.05 newtons. start over. Okay, so I'm going to give an example of gravitational potential energy and then an inelastic collision, me with the trampoline. And it's inelastic because I don't go as high as I originally started. Okay, so then this is 1 foot off the ground, so I'll calculate gravitational potential energy later, and then this is the inelastic collision. Okay. So in my video, I meant to say that I was 1 meter off the ground, not 1 foot. So to find the gravitational potential energy, I would do my mass, which is 58.89 kilograms times 9.81, and I would multiply that by 1 meter. And then that comes out to be 577.7, which is, since it was only 1 meter, it's kind of like the same as the force of the earth pushing up on me.
Go.
Okay. This is for the spring constant, and those are springs. And when I'm bouncing on the springboard, when I jump up, I have gravitational potential energy, and then as I hit the springboard, that changes into elastic energy because I'm compressing the springs. And that gives me, and then the energy switches back to gravitational energy when I pop back up. And here's some other videos that I took for this project, but didn't really use. And this is Julia, and she has inertia because she's moving and she has mass. And that's her fall. Okay, so I exert the same force on the beam that the beam exerts on me. The end.